Hello everyone. Today, we're diving into a crash course on the foundational chemistry of life, where we'll explore the biochemical symphony orchestrating the functions of all living organisms. Welcome to the chemical basis of life. Here you'll find a breakdown of today's topics and their corresponding sections, designed to guide you through our discussion. We'll use this as a reference throughout the course. Let's begin with the elemental components of life. Organisms are composed of elements, usually combined into compounds. An element is a substance that cannot be broken down to other substances by ordinary chemical means. Each element has a symbol made up of the first letter or two of its English, Latin, or German name. For example, the symbol O comes from the English word oxygen. The symbol for sodium, Na, is from the Latin word natrium. A compound is a substance consisting of two or more different elements combined in a fixed ratio. For example, table salt has equal parts of the elements sodium and chlorine. Pure sodium is a metal and pure chlorine is a poisonous gas. Chemically combined, however, they form an edible compound. Table salt is an example of organized matter having emergent properties. A compound has characteristics different from those of its elements. Oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus make up about 99% of living matter. Trace elements are common additives to food and water. Trace elements make up less than 0.01% of human body weight. They include fluorine, iodine, and iron. Iron is vital for energy processing and for transporting oxygen in blood. Atoms consist of protons, neutrons, and electrons. A proton is a subatomic particle with a single positive electrical charge. Protons determine elements. A neutron is electrically neutral. Neutrons determine isotopes. An electron is a subatomic particle with a single negative charge. Electrons determine chemical behavior. Radioactive isotopes can help or harm us. A radioactive isotope is an isotope in which the nucleus decays spontaneously, giving off particles and energy. Radiation from decaying isotopes can damage cellular molecules and pose serious risks to living organisms. But radioactive isotopes can be helpful. Radioactive isotopes are valuable in basic research and medicine. Now, let's delve into one of the fundamental concepts in biochemistry, chemical bondings. The distribution of electrons determines an atom's chemical properties. Electrons can be located in different electron shells, each with a characteristic distance from the nucleus. An atom whose outer electron shell is not full tends to interact with other atoms and share, gain, or lose electrons, resulting in attractions called chemical bonds. Covalent bonds join atoms into molecules through electron sharing. A molecule consists of two or more atoms held together by covalent bonds. An atom's electronegativity is a measure of its attraction for shared electrons. In a nonpolar covalent bond, electrons are shared equally. In polar covalent bonds, such as those found in water, electrons are pulled closer to the more electronegative atom. Ionic bonds are attractions between ions of opposite charge. Electron gain and loss create charged atoms, called ions. Sodium fluoride is an ionic compound. Note that the names of negatively charged ions often end in "ide", such as fluoride. Hydrogen bonds are weak bonds important in the chemistry of life. The slightly positively charged hydrogen atoms in one polar molecule may be attracted to the partial negative charge of a fluorine, oxygen, or nitrogen atom in a neighboring molecule. Thus, each water molecule can hydrogen bond to as many as 4 partners. Hydrogen bonds help to create a protein's shape. They also hold the two strands of a DNA molecule together and play key roles in translating hereditary information into proteins. Chemical reactions make and break chemical bonds. In a chemical reaction, the starting materials are called the reactants. The materials resulting from the chemical reaction are the products. The composition of matter is changed as bonds are broken and formed to convert reactants to products. Notice that the same numbers of hydrogen, carbon, and oxygen atoms appear on the left and right sides of the arrow, although they are grouped differently. Chemical reactions do not create or destroy matter, they only rearrange it in various ways. Water, often called the universal solvent, plays a crucial role in sustaining life. Now, let's delve into some key properties of water. Hydrogen bonds make liquid water cohesive. Cohesion is the tendency of molecules of the same kind to stick together. Cohesion is much stronger for water than for most other liquids. Surface tension is a measure of how difficult it is to stretch or break the surface of a liquid. Hydrogen bonds give water unusually high surface tension, making it behave as though it were coated with an invisible film. Cohesion creates surface tension and helps water to move from plant roots to leaves. Water's hydrogen bonds moderate temperature. Heat is absorbed when hydrogen bonds break and released when hydrogen bonds form. This helps keep temperatures relatively steady. As the most energetic water molecules evaporate, the surface of a substance cools. Ice floats because it is less dense than liquid water. In liquid water, hydrogen bonds constantly break and reform. In ice, stable hydrogen bonds hold molecules apart. Floating ice protects lakes and oceans from freezing solid, which in turn protects aquatic life. Water is the solvent of life. A solution is a liquid consisting of a uniform mixture of two or more substances. The dissolving agent is the solvent, and a substance that is dissolved is a solute. An aqueous solution is a solution in which water is the solvent. Polar or charged solutes dissolve when water molecules surround them, forming aqueous solutions. The chemistry of life is sensitive to acidic and basic conditions. A compound that releases hydrogen ions in solution is an acid, and one that accepts hydrogen ions is a base. The pH scale ranges from 0, most acidic, to 14, most basic. The pH of most cells is close to 7, neutral, and is kept that way by buffers. Scientists study the effects of rising atmospheric CO2 on coral reef ecosystems. The acidification of the ocean threatens coral reefs and other marine organisms. The search for extraterrestrial life centers on the search for water. The emergent properties of water support life on Earth and may contribute to the potential for life to have evolved on other planets. In conclusion, the chemical basis of life underscores the intricate molecular interactions that govern biological systems. By understanding the principles of chemical bonding and the properties of water, we gain insights into the biochemical symphony that sustains life. Thank you all for your participation and engagement. Feel free to ask about anything we've covered in the comments below, or share your thoughts on the fascinating world of biochemistry. Have a wonderful day. Thanks for watching. Don't forget to like and subscribe.